Good morning everyone. Welcome to the lecture series of VLSI Technology KEC 053. So the subject we were covering in these video lectures are VLSI technology, and we are covering the second unit as per the AKTU. In the last class we have covered the silicon on insulator, that what are the advantages of silicon on insulator, why we prefer silicon on insulator over the CMOS technology. So in this lecture we are going to study that how we can fabricate a silicon on a sapphire and how we can done the evaluation of the epitaxial layer. So the silicon on sapphire is technology is a heteroepitaxial process, right? The epitaxial process we have studied that in case of heteroepitaxial process, when we need to grow some another compound over some another orientation, it is known as heteroepitaxy. And we know that your sapphire has the hexagonal structure and silicon has the diamond structure, right? So orientation of both the materials are different, and we need to grow silicon on the sapphire hexagonal. So we need to grow the diamond orientation over the hexagonal orientation. So both the orientations are different. So that is why it is named as heteroepitaxial process for metal oxide semiconductor ICs. So it consists of a very thin layer, usually in the range of 0.6 micrometer of silicon, which is grown over the sapphire, and the compound name is Al2O3. This SOS is a part of silicon on insulator SOI family, where typically a high purity artificially grown sapphire crystal are used as a base material, and the silicon is usually deposited by the decomposition of silane gas. We can use this silane gas as a starting material, so that we can on a heated sapphire substrate. Here we can use the chain reaction also, where we can have some HCl gas as a residual, and second method we can also use that pyrolytic. Pyrolytic reaction we can also use, where we don't have any HCl gas as a residue. So the advantage of sapphire is that it is an excellent electrical insulator and prevent the stray currents caused by radiation from spreading in the nearby circuits. So when we work at a radio frequency, at a very high frequency rate, chances are there some stray currents will affect the performance of the overall circuit because of the radiations which comes from the nearby circuit. So your sapphire behave as an excellent electrical insulator and will prevent that issue. So this technology faced challenges in the initial year, and this is because SOS process results in the formation of some dislocation, twinning and stacking faults from the crystal lattice between the sapphire and silicon. Because it is a heteroepitaxial process, there will be some dislocations. So that is why this technology faced some channels in the initial years. So additionally, there is some aluminum, a p-type dopant contamination from the substrate in the silicon will be there at the interface. So when we deposit, suppose this is your sapphire and this is silicon, we deposit silicon over here. So some of the dopants may come and deposit over here also, because the process is carried out at a very high temperature. So this is the diagram where we have the substrate, your sapphire is deposited over this. We have the silicon layer where we have the NMOS and PMOS devices. So why the silicon on sapphire technology is important to integrated circuit? Because your sapphire has a very high permittivity, and that can eliminate the interaction between the components. Okay, so because of this factor, high permittivity, it eliminates the interaction between the components. SOS technology can reduce the leakage current and the parasitic capacitance. This SOS can also enhance radiation resistance and reduce the power consumption. So with the help of this SOS technology, we can improve the level of integration, and two-layer wiring can be used. Thus, Sapphire is ideal material for the LSI, VLSI, ULSI, and above that. So for these chips, your Sapphire is the ideal material. So silicon or sapphire technology provides an ideal isolation and reduces the parasitic capacitance in the substrate area. So it is suitable for the high speed circuits, and with the help of this sapphire, sapphire as a dielectric layer, we can have a high speed and low power consumption. So this process is generally used to make all the CMOS circuits. In addition to that, in case of SOS, your circuits and the production everyone can be done on a single silicon layer, because your thermal expansion coefficient of silicon is similar to the sapphire. So everything can be done on a single substrate. So as a starting material, your silicon monocrystalline film with the orientation of this 100 can be grown on the surface orientation of it is 1 bar 0 to orientation of the sapphire substrate by heteroepitaxy. So to grow this material, this should be this is the orientation which we will grow over this orientation. So and at present, your sapphire crystal has become widely used substrate for the grown of semiconductor material. The next topic is the epitaxial evaluation. Now we have grown the epitaxial layer. Now we will study that how this evaluation can be done. This is done for the characterization of thickness, carrier doping, and to check the defect and contamination of the epitaxial layer. So in case of epitaxy, we have this substrate, right? Over this, we have grown the epitaxial layer. We have grown the epitaxial layer. So we need to know that how much thickness is there. Is it as per our requirement? Is it as per the designer requirement? How much is the carrier doping is there? How many defects are there in the epitaxy, and is there any contamination or not? So this is done by a thickness method. The first one is your non-destructive method. In this method, your infrared reflection with the help of monochromatic light source is done, and the study is done for the interference patterns of the reflected light source. So in this process, we will pass a light source with a very less incidence angle, that is approximate 1 degree C. The angle of incidence is kept less so that this incidence ray, it should not penetrate inside the substrate. It will only penetrate up to this level. Okay. So with the help of this, it will be reflected back right after at some angle. So angle of penetration should be kept very less. So and the interference patterns are studied by using this method, and this method is done by using the IR spectrophotometer. The next method, we have the Fourier transform IR spectrometer FT-IR method. This method uses the interference principle along with the broadband IR source. It is used to measure the spectral output of the interferometer. So this is the formula. By using this, we can have the thickness. We can have the thickness of the epitaxial layer. This formula states that it is Pn minus 1 by 2 plus Pi Wn 2 n square minus sine square a raised to the power 1 by 2, where Wn is the position of maximum and minimum in the spectrum in micrometer, and this n bar is the index of reflection, a is the angle of incidence light, Pn is the order of maximum and minimum, Pi is the correction factor that depends upon the substrate. So an automated approach is used to measure the these patterns. It is known as Michelson Interferometer, and this samples all the wavelengths simultaneously, and the output is called the interferogram. This output is the Fourier transform of the reflectance spectra, which is obtained on the photospectrometer. So thus the thickness can be obtained from the interferogram or with the help of computer. Your computer will convert it into Fourier transform and then calculate the thickness using the above equation. The thickness with this method we can measure up to 1 micrometer to several hundred micrometer with the time span of 5 seconds. So the structures, next is when there are some structures which are not responded to this infrared measurement. So that can be their epitaxial stacking fault nucleated at the substrate, which are linearly related to this formula. Your thickness is C1L, where T is the layer thickness, L is the size at the fault, and C1 is the orientation dependent constant, which is 0.707. It is fixed for each orientation. This C1, the value of this C1 is orientation dependent. It is 0.707 for 100 orientation and 0.816 for 111 orientation. Next is epitaxial doping. So the uncertainties of doping kinetics, some background effects and auto doping effects, they do not allow the doping in the layer as precise as we want to be established simply on the basis of the flow of the reactor. So there are 3 types of electrical measurement we can use to check the doping. First one is your sheet measurement, second one is the capacitance voltage graphs, and the third one is the spreading resistance. So these are used for the measurement of doping level. In the first method, in the sheet measurement method, a control wafer technique is widely used, in which a lightly doped wafer is placed, slice of conductively typed placed opposite to the layer which is to be grown inside the reaction chamber. After that wafer is placed, we use the 4 probe method. We have this we have 2 substrate, one is lightly doped and this is the substrate where we need to grow the epitaxy layer. Okay. So 4 probe method is used. We use 4 probes. 4 probe method is used to measure the sheet resistance of the layer. This sheet resistance is then converted into the resistivity by using the infrared thickness of the adjacent product slice. So this method, but the drawback with this method is highly inaccurate. So we cannot use this method for the doping to check the doping concentration. The second method is done with the help of Diode Cv measurement. In this Diode Cv measurement technique, a diode on the epitaxial surface is reverse biased to create a depletion region. The increase in the measured capacitance delta C with the increase in applied voltage, it depends on the density of the carriers which are swept out of the depletion region. So by using this formula, we can check the doping profile, where Xc is the permittivity of silicon into area divided by capacitance, C is the capacitance, V is the voltage, Q is the charge of the particle, A is the diode area, This is the dielectric permittivity of silicon, N is the doping density, X is the depth, and CF1 and CF2, here this CF1 and CF2 are the correction factor for diffused junction and the depletion layer, which is created with the help of reverse biased. Next, last method is the spreading resistance measurement. With the help of this method, we can measure the resistivity of wafer by surface measurement. Over the surface of the wafer, we will calculate the resistance at certain points. So, spreading resistance is measured by lightly doped probe, which are kept apart at 10 to 100 micrometer. So, and in a uniformly doped sample volume, your spreading resistance under each probe is calculated by this formula. Your sheet resistance is rho upon 4A, where A is the area. Lastly, the wafer is examined with the unaided eye. We can examine the wafer with the unaided eye under the high intensity light to judge the quality of the epitaxial layer. We can reject the wafer if you find some spots, strain, gaze or scratches which are visible to the eye, right, which are visible to the unaided eye. So, we can directly reject those wafers. In addition to that, your inspection can be made at magnification from 50 to 200 to evaluate the microscopic defect densities like stacking faults and tri-pyramids. And another useful technique is to etch the wafer into the solution to determine the dislocations. Okay. So, these are the evaluation techniques which we can use to evaluate the quality of the epitaxial layer. So, in this lecture, we have studied about the silicon on sapphire technology, that what are the advantages of silicon on sapphire technology, where we can use that technology. We can use that technology when we are working at radio frequency circuits, in analog circuits. So, this is highly advantageous in the communication part. And in the last part of the lecture, we have studied about the evaluation of epitaxial layer, that how we can study the quality of the epitaxial layer, how we can measure the contamination defects, doping density, doping concentration, and the thickness of the epitaxial layer. Thank you so much for the lecture.